Oh, okay. Let's continue our lectures devoted to the structure of the infinite dimensional spaces, where we want to consider random elements and probability distributions. Last time we discussed the probability of Banach spaces, and now it's time to consider one of the most powerful tools for description of the elements of the Banach space. This is linear continuous functional. What is the idea of our considerations today? Suppose that we have a Banach space with the norm B, with the norm here, and we want to have a simple description of the elements of this space. Why I'm talking about simple description? Because the Banach space can be rather complicated. We already have seen such examples as, for example, space of all finite measures on some measured space, or space of just bounded sequences, or bounded measured functions, or continuous functions on some compact, and so on. So this space can be much more rich than the space Rn. When we have a usual finite dimensional space, then if we have here element, it is useful and sometimes fruitful to put into correspondence to this x its coordinates in some bases. So x1, xn, maybe x is sum from k equal 1 to n, xk, en, where where ek is the linearly independent system of elements of R. Usually such system that every element of the space can be described as follows is called basis, and after such after we get such correspondence, then we can walk instead of this space, instead of the element of basis, we can just walk with the finite sequences of numbers, and we already have very powerful tools to work with them. But if we have a Banach space, then what we can put into correspondence to the element of Banach space? It occurs that even in good spaces, one cannot achieve the expansion like this. Of course, we can expect that it will be infinite series and so on, but still there are spaces where we have not such expansion. Even if we want to substitute our x by the sequence of some coordinates, it doesn't work. So we need something for description of our elements from Banach space, and we already at least formally understood that it cannot be in general a sequence of coordinates, but what it can be. And here we still can use something which is very similar to coordinates, but without basis. And this is the notion of the linear continuous function. So we just will use such definition that function f, which is acting from B to the set of real numbers, is a linear continuous function if the first one, it is linear, so f from any combination like a1 x1 plus a2 x2 is equal to a1 f from x1 plus a2 f of x2, and another one f is continuous.
At the moment, it doesn't matter which field we consider for A1 and A2.
Excuse me, we just use real Banach space, so so we use the case much more appropriated for considering random elements and measures.
Mm-hmm.
Of course, the complex Banach and Hilbert space are more close, for example, to quantum physics.
Mm-hmm.
But usually, even we want to consider Gaussian random elements in complex Hilbert space, we face a lot of new interesting problems. So we will avoid these problems in our course and study only only Banach spaces on the field of real numbers. So we have such a definition, and let us consider a few examples of such functionals. Maybe most important for us example is the following. Suppose that our Banach space is a space of continuous functions on the interval 0, 1, with the usual norm. I just put here infinity, and the norm element from here is the maximum of its values, maximum of the absolute value of its values on 0, 1. Now let us consider f of x is equal to x at the point y1/2. Then this is a linear functional, and it is evident that it is continuous. Why? Because one can see that f of x is less or equal than norm of x, which is, as I said, equal to max of the value, absolute value of xt on the interval 0, 1. So one can see that this f is a linear functional. Maybe it is evident that the same happens for any t. And what we can see already, we can see that, for example, such a map which maps a function f to the space Rn is also linear and continuous. And maybe those of you who already studied random process theory recognize that the familiar thing because when we consider random process, then we consider its sets of finite values, of finite number of values in some points of the set of parameters, and we discuss finite dimensional distribution. So you see that in the case when B is space of continuous function, we get as good examples of continuous functionals, we get the values which we already here will use when discuss distribution of the random process. So this gives us an idea that maybe linear continuous functionals also will be useful when we will consider distribution of random elements in arbitrary Banach spaces. Of course, even in this space, we have more complicated continuous linear functionals. Let me show. Suppose that we have a thing. But now consider the following functional. Here's the integral from the x, which is against some function, and now also is it is easy to check that this functional is linear and continuous. Please do it by yourself. So we see that we have a rich enough set of linear continuous functions, and let us think how we discuss these functionals. It occurs that for linear function to be continuous, it is equivalent to be bounded on the unit ball. So we introduce the norm of the linear functional as a sup with respect to B01 of f of x. Here B01 is a set of such x. Norm of x is less than 1. One can use here the following modification. It does not matter because we have here sup.
But probably there should be an absolute value of f of x, or
you know, this is not necessary because this set is symmetric.
okay.
So if we have here x, we have minus x, so we already have proven. But of course, this is a good remark. So let us know that due to the symmetry of this ball, we have here equality. This is the same that absolute value of x. Another remark which must be done here is that supremum here is important. It cannot be substituted by the maximum in general. We will discuss further the reasons. The reasons is related to the smoothness of the norm in the initial Banach space, And by the way, it is related to some deep probability properties of the space. We will discuss it in the future. But now I think that you can try to find example when we of such linear functionals when we cannot put here max by use. It will be a good exercise. So if we have here norm, as I said, then maybe we can organize a space of linear functionals. It is true. So one can organize B star. We will call it conjugated space. This is a set of all linear continuous functionals. On our initial space B, this with the norm of F sup over union wall 0, 1 F of X. Okay, so we can organize normed space, and it occurs that it is a concrete normed space. So every Cauchy sequence has a limit in this space, and one can check. Again, this is not hard to check by yourself, that F with this norm, B star with this norm became to be a Banach space. This Banach space. It is interesting that the fact that it is Banach space does not depend on the initial space. One can define linear continuous functionals on the normed space, which is not Banach, which is not complete. But this is just very easy problem, because we always can have completion, easily extend our linear functional in the completion by continuity. So this space is always a Banach space. Before to give you examples of conjugated space, and before to discuss how we will use it, let me recall the most important fact from the theory of linear continuous functional. This is Hahn-Banach theory. This theorem says exactly the following. Suppose that we have Banach space B, and we have A, which is a subset of B, and A is a linear subspace. It's a linear subspace. So it is closed under the linear operation on its elements. Suppose that we have function f which is acting from A to R, which is linear and continuous. So this is continuous functional on A. Is linear and continuous. Then one can define norm of F as we did it before. So one can define norm of F, but I will put here A to emphasize that we just have F which is defined on the subset of B. Norm of F with this index A, as usual, sup or B 0, 1. Again, I will put here index A in order to emphasize and work with such subset. Here is f of x. And see what happens. This Hahn-Banach theorem says to us that there exists the linear function, continuous linear function that belongs to B star such that two condition holds. First, F restricted onto L coincide with F. So F with tilde is the extension of our linear functional to all space. And another one, which is very beautiful, that norm of F with tilde is equal to the norm of F. So one can say that any linear continuous functionals on the subspace can be extended to linear continuous functional of the whole space, keeping its norm. There are a lot of generalization of this theorem related to semi-norm, family of semi-norms in the space B and so on. We will not mention all this extension because this is nice and rich theory, and it is not main direction of our considerations in these lectures. But I heavily advise you to check this theory because it is really nice and beautiful. What is important for us in application of this Hahn-Banach theorem? Most important consequence for us in studying the random elements and probability distributions in Banach space is the following. Due to this Hahn-Banach theorem, linear functionals can play a role of coordinates or values in the fixed point of random processes. So this Hahn-Banach theorem will give us possibility to speak about finite dimensional distribution, because it easily follows from this theorem that continuous linear functional on the Banach space distinguish between different elements of the space. Namely, we will have such, from the first look, simple but very important consequence. This is like a corollary. Suppose that maybe for every element x which belongs to P, there exists such f which belongs to P star, that f of x is equal to norm of x, and that norm of f is equal to 1. You see? So for every element, we have such continuous functional which gets such value on the element and has its own norm equal to 1. By the way,
So does it mean that f of x can be bigger than 1?
F of x, yes, surely, norm of x can be sufficiently large.
Yeah. Okay.
By the way, I use here norm here denote the norm in the space B, and here norm denote the norm at the space B star. I think that it is not confusing. So how to prove it? It is easy. Just consider the space L, which consists of only this will be only one line. It is the space like this: Tx, when T belongs to R. When we consider such elements in our space B, it is easy to understand that this one-dimensional subspace, and then we can think that we can define here continuous functional. How we can define it? Just put f of Tx is equal to norm of x multiply on T. Then it's easy to see that if we consider now norm of Fl indexed by L, it will be like following. It will be the sup. I must put here unit ball in this space. What it will be? It will be like T, which is taken from 1 over norm of x minus plus 1 over norm of x. Yeah. This is and here f of Tx. When I consider T from there, Tx has a norm which is not greater than 1. Yeah. Then, due to this description of our functional, I will do it by eraser. I just substitute here the norm of x multiplied by t, and one can say that it is equal to 1. Okay, one can see that it is equal to 1. So we have such a functional, and now we apply Hanumanov theorem, and we get a functional which we need. F with tilde, which we need. So why I am saying that it is a very important property? Because, for example, now, if we consider two elements which are not equal in our space, then always exist element f belonging to B star such that f of x is not equal to f of y. Yes, it is enough to take the element from this corollary related to x minus y. Yeah. So now we understand that the set of this continuous linear functional is sufficiently rich to describe elements of our initial space B. Even more, we have very interesting. We have very interesting different conclusions about this situation. Let me show you some of them. For example, we discussed with you some properties of Banach spaces related to two basic things. One is dimension, another one is separability. When we discussed dimension, we already found that if dimension of B is less than infinity, then B is equal to R, and with a special norm, any norm in Rn can be described by the convex body, which is symmetric with respect to origin, and this will be a unit ball in our space. For example, one can take usually Euclid distance. One can take distance which is related to the sum of absolute values of coordinates. One can take the distance which is related to the maxima of absolute value of coordinates, and so on. I just mentioned this structure of the finite dimensional Banach space in order to give you a very good exercise. Please find the norm in the conjugate space. So one can check several things. Firstly, please check that Rn with arbitrary norm, which is defined by this convex body, when we take a star, it is equal again Rn, and find the norm. Find the norm, please. At least in these cases, it is not hard to do. But of course, it is zero to find it in general case. Okay. So this is about the finite dimensional space, and what is interesting and important for us here, this simple equality. Maybe you understand that if I take element x, which belongs to our Rm, then this element is described by its coordinate, and I can consider coordinate functions. So I can consider fi of x, which is equal xi, and the set of these linear continuous functionals completely describe our element x. Now let's go to the arbitrary Banach space. First of all, let me note that due to Banach theorem, we have interesting conclusion that for all x in our Banach space, we have that norm of x is equal to sup over norm of f is less or equal than 1 f of x. Yes. This is trivial when we have Banach theorem, because for such f, that norm of f in conjugated space is less than 1, f of x this absolute value of f of x is less than or equal than norm of x, norm of f. Yeah. So this is due to the definition of the norm of the linear function. But from other side, there exists, by Hahn-Banach theorem, we discussed, there exists special f0 such that norm of f0 is equal to 1 and f0 of x is equal to 1. Excuse me, norm of x. So we have one. So even one can put here max instead of supremum, and we have a good tool for obtaining of the norm. But from the point of view of using this this relationship, we need some simplification, because usually in complicated situation we don't know this f0, and even it is not necessary to calculate it. But what we need to substitute this set of all functionals which have norm of less than 1 by the countable sequence. And it occurs we can do this in good cases. So let us simplify. Let us simplify this relationship for our hypothesis. Suppose that our space B is separate. Suppose that B is separate. So one can have the sequence xn, which is a subset of B, which is dense. Then let me take for every xn, I can find by Hahn-Banach theorem the such functional fn, which belong to B star, that norm of fn is equal to 1, and fn from xn equal to the norm of xn. Such functional exists due to the Hahn-Banach theorem, and now I claim that we can simplify the equality for the norm of the element in our space B. Namely, the following relation holds. Norm of x is equal to sup over n f and x. Yeah. Let's check. Let's check. Since xn is dense in our space, then for every epsilon which is positive, I can find such n greater than 1 that norm of xn minus x is less than epsilon. From here, I can get two conclusions. First one, that no absolute value of norm of xn minus norm of x is less than epsilon. Yes, this is just real inequality. And the next conclusion is due to the following relation from the construction of the functionals Fn. Namely, from here one can conclude that from the first one and this one can conclude that from this one, excuse me, that absolute value of f of xn minus f of x, which is equal to absolute value of x, it is linear, of xn minus x, is less or equal than norm of f n, excuse me, fn, norm of fn multiplied with the norm of xn minus x, and one can check that this is less or equal than epsilon. Yes. From other side, now let us use that fn from xn is equal to norm of xn. So now we have that absolute value of norm of xn minus fnx minus fnx is less than epsilon. Now let's combine these inequalities, and we get that norm of x minus fnx epsilon value is less than 2 epsilon. From here, one can check the sup over n fnx is greater or equal to norm of x. From other side, due to fn, norm of fn is equal 1 always, this is less than equal. So we have equality which I said. Now we understand that in separate Banach space, maybe we have no coordinates, but we always have a counted set of linear functionals, which give us all information about our elements. Let me get from here the first sentence, which is closely related to our course, namely, let us consider in our Banach space B with norm, which is separate now, two sigma fields. One is Borel sigma field. So, as usual, I will denote by this calligraphic letter B is Borel sigma field. Borel sigma field in our space. This means that B is the smallest sigma field containing open sets. And we consider another one. Let us denote it by F. F is a sigma field generated by B star. It means that F is equal to sigma field by this one. Here is a set of function, and this is a smaller sigma field such that all these functions are measured with respect to this sigma field. Then I am claiming that these two sigma fields coincide in separate cases. So this is a lemma that this Borel sigma field is again emphasizing that this is only in the case of separable Banach space. How we prove it? It is evident that F is included into B because B star consists of continuous linear functions. If we take any family of continuous functions, then they generate the sigma field, which is included into the Borel sigma field because of the characterization of the continuous function, continuous mappings between two topological spaces. The pre-image of the open set is also open. So we have such inclusion. So what we need only inclusion in the backward direction. Again, let me say what we need. We don't need to check that every set from here belongs to the sigma field. Because this is sigma field too. So if I just take here family of open sets, it will be enough. Yes. Next, you remember we are working in the separable space. So if this is a cloud open set in our Banach space, this cloud can be represented. This open set J can be represented as a union of open balls. So J is a union of counted family of all the open balls from k equal 1 to infinity, b x k r k. Here I use separability. These open balls can be taken from the family of such kind. We just took here dense set, and as radius we can take any rational number which is positive. Yeah? So then one can choose appropriate balls which from one side belong to J, from other side cover Z. So we have such a representation, and due to this, because this is a countable union, I can substitute this open sets by balls, all balls. So here is B, X, R, X belong to B, R belong to 0 plus infinity. Okay. But due to the linearity, it is enough to check that B01 belongs to our. So I will discuss the following. That this belongs to F. Also, let me say that it is enough to check this one when we have closed union ball. Because if we prove that closed balls belong to F, it is trivial to get open balls as a union of expanded closed balls. Yeah, so it's enough to check this. But this is exactly the set of such X that sub n Fn of X is less than or equal to 1. That's all. Yeah. Because Fn, this sequence constructed in the previous lemma. Then here Fn, of course, are measured. Supremum of the countable sequence of measured function is measured. And then this is pre-image of the measured function. So this set is measured with respect to F. This ends our proof. So one can see that in case of separable Banach space, continuous linear functionals give us a good tool to discuss random elements in this space. Further, we will discuss the random elements in terms of values of continuous functionals from these elements. It occurs that this is enough. We see that the Borel sigma field is generated by the continuous linear functionals. Okay, that's all for today. Thank you very much for your attention. Maybe some questions. If there are no questions, thank you again.